Hello. So I want to go over this assignment for the consumption insurance investment dynamic programming solution. And we're doing the backward recursion. Now take note of this here. I do expect you to use AI heavily. And one of the main purposes of this assignment is for you to learn to use AI effectively in the mathematical context. So in your submission, send me the links to all of your AI transcripts. I want to review your methodology. Are you using AI effectively? Using AI effectively involves dialogue. One thing I keep coming back to is at every stage you need to be asking yourself, is AI giving me the right answer? Is it telling me something that makes sense? So there is definitely dialogue involved. I don't care which AI you use, but I do want to have your transcripts. Right? So in this assignment, we're introducing an alternative implementation, and we'll compare the performance of this new implementation with the old one. Frankly, I think this new one should be better, but I could be wrong. So it's good for us to compare. It's always good to compare alternatives. Now, I talked about this before, that if I know my wealth at time t and my wealth at time t plus 1, then there is some relationship between my expenditures. There are two types of expenditures, consumption and insurance. And because other things are known, if I know how my wealth changes, I can find a relationship that relates C and B. And the relationship does have this form, C plus B equals Q. And Q will depend on my wealth at the current time, my wealth at the next time, and some other parameters, including my income and so on. So if we're doing the deterministic case, in this case, my investment return is R prime, where R prime will simply be the maximum of your bank rate and your stock rate. So you can just set one value for R prime in this deterministic model. Right? So your expression for C plus B will be a quantity Q that also depends on R prime as well as these wealths and the income, right? So that's what you want to do here. Now, why are we doing this? Well, you'll see in a minute. So just bear with me. I want to follow the discussion here. So 3.1.2 says the utility calculation. We've seen this before. This is part of the overall specification. There's the utility involved with the expenditure during this time interval, during year T. We can call this year T, all right? So you get the utility from consumption and the utility that accrues from insurance if the person dies. So that's the utility associated with that particular year. Now, of course, the wealth is also going to grow, but we don't want to consider that right now, right? So if I do know that I have wealth x sub t at time t and wealth x t plus 1 at time t plus 1, let me change this, sorry. I think I want to use consistent notation. What I was saying here was x paren ti. I think that's more consistent notation. Please, I know the notation is complicated, and sometimes different letters will be used for the same thing. For instance, this C and B here that I use are just for generic C and B, and not looking at any particular time, right? So if I know the difference in wealth, or the wealth at this time and the wealth at this time, I can find an equation for the optimum, right? Because I want to maximize this, and I also know this relationship with C and B, right? So in fact, you can eliminate C from the equation and find the optimum value as a function of B, right? Now, when you eliminate C from the equation, you will not be able to solve for B, but you can find an equation that B must satisfy and then obtain C in terms of B. In fact, the equation that you can satisfy will have this form, right? B will appear on both sides, but it's an algebraic equation, and it can be solved. You could graph this as a function of B. If I move this term to the other side, I could graph this as a function of B, and then I could find the root. All right, so we'll have to solve this one numerically. Now, these parameters, W1, W2, W3, W4, they all depend on the model parameters, and we know as before that Q depends on the differences between wealth and other model parameters. So you'll have to express these W's in terms of the other model parameters. In particular, the exponents depend on the epsilon, which is the, that's given up here. The epsilon is the utility exponent for legacy, and the delta is the utility exponent for consumption. Right? So these exponents are going to depend on my values of epsilon, delta, and perhaps other quantities as well. Okay, so let's get back there. Okay. So you need to give expressions for these, right? So this should enable us to be able to find the optimal C and B combination, given that I know from this, that I go from this wealth level to this wealth level at time t. All right. So the idea for this algorithm, and I think I indicated this picture before. Let's see, I have to do this, and I have to make it bigger. Okay, there we go. And then I have to do this. Okay. All right, so the interpolation algorithm, and this algorithm is the first algorithm that we did. I'm calling that the interpolation algorithm. Now, at one stage, that means I would have levels for x sub t plus 1. And I guess I call this t plus 1. And I'm calling these different levels I prime. So I have different levels here. And then I have these levels x of t. Okay. All right, so for the interpolation algorithm, I'll use a different color here. For each value here, I choose some different options for C and B. Okay, so I choose some C and B options. And I'll end up at different points here, and then I interpolate these values. So I'll have to interpolate these values. All right, and I discussed that previously in a previous video. Okay, so that's the interpolation. Now, if I do another approach where I don't interpolate, instead of doing that, let's find a good color. I guess brown is good. Is that thick enough? Yeah, that's fine. Here we go. So I can do a non-interpolation approach where I know I start here and I only allow myself to go to these grid points. Now, if these grid points are closely spaced, then that will still be representative of all the strategies. Now, for this particular transition, I'll use x of ti and x of ti plus t plus 1 I prime to determine the optimal C and B for this transition. So I don't need to try different values of C and B. If I just know the transition, I'll use the transition to determine the C and B for me. So, and as I said before, the method will be, first you determine B using the algebraic equation, and then you determine C as a function of B. But the transition gives me my Q, because Q is a function of the difference between these two. And then I can determine C and B. So it's a different way of enumerating the different transition possibilities. And it seems to be more efficient. And it avoids interpolation. So it has several advantageous features. Furthermore, there's a lot of these transitions are not possible, and you don't even need to compute them. Right? So that's also going to save time. So I'll just say there are many impossible transitions, right? I can't transition from way down here to way up here, because that would give me Q value, which is negative, and that's not possible. So there are many transitions that are not possible. Because Q has to be bigger than 0. Actually, Q has to be between 0 and 1. So I also can't have transitions with too much consumption and insurance. So, all right, so let's see what we got here. Let's continue. So here I describe how we can modify the algorithm, the previous algorithm, and I just copy-pasted the previous description and made these changes. All right, but the idea is, as I mentioned, you keep the same levels for each time based on, so if I'm trying to compute at xt minus 1, so I talk about how to compute the transitions from xt minus 1 to xt. And then you use the same method to go backwards from t minus 2 to t minus 1, etc. Okay? So please go ahead and implement that algorithm. And I do recommend you put this algorithm in a separate notebook. If you put everything in one notebook, it's going to get very, very, very long. And if we do debugging, we probably want to isolate the algorithm that we're debugging. There may be some back and forth, and I can give you some indication on how to do that if you have problems with your code. All right, so here's the next section. This is more about modifying the model than about programming. You always need to be thinking about the model as it relates to reality. Now, we do have this parameter that we call A. That's the premium to policy ratio. That's what the insurance company sets. It's kind of the rate of payment if the person dies. So let's consider this scenario from the point of view of the insurance company. If the insurance company sets a premium payout ratio of A, then the company's expected profits from an insurance policy that costs B dollars per year is B minus B over A times PD, where PD is the probability the customer dies during that year. All right, so I ask you why this formula gives the insurance company's expected profit. All right, think about what this means, but this is the expected profit for the insurance company. And of course, the insurance company wants to make that as big as possible. Suppose the insurance company sets A as PD over 1 minus V. Explain why V gives the company's profit margin. Okay, so of course the company wants a positive profit margin. If V was negative, then the company would lose money. Right? So I do want you to modify your two algorithms. You should have two different notebooks with two different algorithms. Modify them so that the premium payout ratio is time dependent and has this form. Okay, all right. All right, so let's improve the efficiency of our algorithms. We have designed the algorithms without really thinking too much about the efficiency. I did try to design the levels of X in order to be efficient, but now that we've done a little bit more work, we can improve that. Okay, so the algorithms we've designed are very slow because they require expensive calculations. Expensive in this context means they require a lot of computation. And so in this section, we're going to give some strategies for making both algorithms much faster. All right, so first we go back to this relationship for B and relating B to Q, which is actually C plus B. All right, we had this above. And you can see what the form of this equation is. B is the unknown. So what you have is you have Q minus B to some power times, and this, for the purposes of solution, this is treated as a constant. And then you have equals B plus a constant over here. All right, so the form of the solution is this. So ask AI for a fast way to do this in Python, and one that's not particularly accurate. All right. So in this case, it's also useful to know what the range of the values are. Here, Q is between 0 and 1 because it's equal to little b plus little c. It turns out that W1 is bigger than 1. This big W2 is bigger than 0. And A is quite small, about 0.01. So you don't need high accuracy, maybe 0.1%. Okay. So get an algorithm from AI that can solve this quickly, because we're going to be solving this a lot of times, thousands and thousands of times. The other thing you need to tell AI is that we only want solutions between 0 and 1. We're not interested in any other solution because any other solution would be not practical. Now, I have kind of passed over the question of whether this value of B is going to give me a maximum or a minimum. It's pretty clear intuitively it's going to give a maximum. If we run into problems, we may have to go back, but we'll just assume at this point that if I find this solution, which is the place where the derivative is 0, it's going to give me a maximum value. All right. So the form of this equation suggests a redesign of both algorithms. In particular, if we use the same levels, instead of using different levels for the different times. All right, so here I should say this one here. See, this depends on XTI. Now, if I reuse the XTIs for all times t, I only need to compute this once. I don't need to compute it for all different times. It's just set. Okay, so that's a nice feature. So we're going to modify the programs so that the same levels are used at each time. If you remember, I didn't do that on purpose previously, but now it seems like that's going to be a good idea. Whenever you do an algorithm design, sometimes you have to make some provisional choice, and then you find out later it's not the best choice. All right, so we want to set our levels of x. We have n levels, and we're going to set this by x max over n, 2x max over n. So these are evenly spaced levels, where x max is the maximum wealth at time t. Right, the maximum possible wealth is the wealth that the person accrues if they don't spend anything. All right, and of course, if times are less than capital T, the wealth will not be that large, but we just don't need to use those extra levels. Okay, so we'll only use those levels that are less than the maximum wealth at time little t. All right, so you will also find the expression for Q has an XTI in the denominator. All right, when you do compute this value of Q. So, and division is very slow in Python. So if we reuse the same levels xt for each t, we can just compute 1 over xti once and store it in an array. Then when we want to divide by xti, we simply multiply by the reciprocal. Now that's a common trick in programming, right? But it will make your algorithm considerably faster. Okay, so that's another aspect that we're going to change in our algorithms. Right now, here we had this value here, which I have been kind of vague about, but this value, it turns out that this value depends only on t, but not on I. So this W3t can be computed once for each t and reused for all I. Okay, we're trying to find commonalities between the calculations. So we don't want to recalculate things that we've already calculated. Okay. All right, now, we also know that Q is C plus B, so we only need to consider values of Q between 0 and 1. Now, in the first algorithm, we chose NT values of C and NT values of B. Now, based on this result, this suggests that we modify the first algorithm. That instead of choosing NT values of C and NT values of B, we simply choose the same N values of Q for all T. We just choose n values of Q between 0 and 1. Right? And then that will determine the C plus B, and then we use this optimization approach to find out what C and B will be in particular. Right? So that's the strategy. First, you quantize or set the levels of Q. For each level of Q, that tells you what C plus B is. If you know what C plus B is, you can find the best values of B and C, right? All right, so that makes it a lot simpler. We're not having to quantize both C and B, we only quantize Q, right? So that should be better, more simple and faster. Okay. Now, last thing that we have is that the computation of Vx for any number involves raising that number to a fixed power, and similarly for VC. Go back up here and see the evaluation functions are here. I have y here, z, it doesn't really matter, or any variable that I put in here, I have to evaluate that variable to a power, right? And we have to do that many, many times as well. When you're trying to optimize an algorithm, you try to identify the operations that you do often and implement them as fast as possible. All right. So where are we? Okay. All right. So we can speed up the execution a lot by implementing these functions as lookup tables, using lookup tables. That's so instead of doing a lot of calculation, you rely on memory. but you should have plenty of memory for this. The lookup tables will not be so big. So you'll have one lookup table for Vx, one lookup table for Vc. And we don't need very high accuracy. So lookup tables are good when you don't need high accuracy, but you need something very fast. So relative error of 0.0005 is fine. So give this information to your AI, and your AI will give you a reasonable lookup table. All right, so now we want to revise the algorithm, the interpolation algorithm, using the same levels for each t and choosing n values for q instead of values for c and b. In other words, I want you to implement these changes in the interpolation algorithm. And then for the non-interpolation algorithm, we can make similar modifications. We use the same levels for each t. We pre-compute these values for each one of those x levels. In this case, rather than selecting levels of q, you will compute q based on xti and xt plus 1 I prime. These are what are fixed in the non-interpolation algorithm. We only consider transitions, as I said here, only we consider transitions between grid points. Okay, so q is not fixed, but the transitions are fixed. So for each I, we only need to compute q for those values of I prime, which give q between 0 and 1. Right? So you cannot possibly have a transition up here. So that actually limits the number of computations for each one of these grid points. That's a very nice feature. Okay, so you're gonna modify the interpolation algorithm and the non-interpolation algorithm. So you do that in your two separate Jupyter notebooks. You can make another copy of those notebooks, or you just overwrite the ones that you have. I'm not so interested in the intermediate algorithms, but the final algorithm. So you can just have one copy. Well, it's always good to save a backup copy that's working. All right. So every time you have a version that's working, you should save it and make another copy when you're trying to twiddle with it. All right. So at this point, we should have two different algorithms, and we need to give them some stress tests. All right. We need to see how well they do. So at this point, you may find out that your algorithm is not working correctly. So if you've got some problem with your algorithm, it doesn't make sense, please contact me. I think at this point, because we're really breaking new ground, it makes sense to be more interactive. I don't want to hear from you 2 weeks later and you show me your algorithm and it's junk, okay? So if you know your algorithm's junk and it's giving you something bad, let me know and we can talk through it. You can send me the code. We can have a call. What I'm giving you here is very much more like a development environment. This is very close to me because right now I am consulting and we're doing stuff pretty much like this, although much more intensive. But this is kind of giving you a taste of how you do algorithm development. And you see what's a mixture of understanding the mathematics behind it and the implementation, because a lot of the implementation issues are really mathematically based, right? You're looking at how many operations you have to do to compute something. So there are two considerations for any algorithm: the execution time and the accuracy. In this case, accuracy means the algorithm should produce a high value for the utility as possible. We're trying to find the optimum utility. So whichever algorithm is giving me the best utility, as long as it's calculating utility correctly, then that algorithm is better. So in the case of the interpolation algorithm, both execution time and accuracy will depend on n and m. Now, we've replaced the C and B choices with a number of Q levels and the number of X levels. However, in the non-interpolation algorithm, we only have one parameter, which is the number of X levels. Right? So what we want to do is we want to represent the execution time and accuracy for different possible choices of n and m for the interpolation algorithm and different possible choices of m for the non-interpolation algorithm. So here I show you how you can do that. For the interpolation algorithm, you want to make two contour maps, should be maps. Okay. The first contour map, you know what a contour map is. Let's just pull it up just so that we know that we're on the same page. So you can see something like this. Let's look at some images. Right, this is a contour map. Each one of these lines shows when the function takes a constant value, just like these altitude maps here, these constant altitude maps. So that's what I want, a contour map. Sometimes people use heat maps, but I think that a contour map in this case will be more useful for us. Okay, so for the interpolation algorithm, make two contour maps. The first contour map that shows execution time as a function of n on the x-axis and m on the y-axis. So here, I don't need that there, so let's just make that grammatical. Okay, so the second contour map shows utility as a function of the same two parameters, right? So you're going to have n on the x-axis, m on the y-axis, and then for each value of n and m, you're going to get a execution time for the first contour map, and for the second contour map, you'll get a utility. Now, I should say here that what we're going to have to do this is you'll have to choose a number of values of n and a number of values of m, and for each value of n and m, you will have to find the utility using the backward recursion. So I think a reasonable number, so we'll choose 15 values. Let's see, evenly spaced values for n and also for n. Whoops. And you want to choose these, so that means making 225 backward recursions total. So you don't want to choose values of m and n that are too high, because you don't want something that takes a minute to run for each n and m. Maybe something that takes 10 seconds is reasonable, so that can give you a result in an hour. Well, at the beginning, you can try small values of n and m. But you can choose these values. You'll have to judge these values. So maybe I can say, choose a range of values so that it doesn't take too long to generate the graph, but that are big enough to get good results for utility. You do want to get good results for your utility. If you just have values of m and n that are too small, you're going to get junk values. You don't really want to deal with that. So where's that? We saw that there was a misprint there. And we'll fix that. All right. Okay. Now you have two different contour maps, but they're using the same parameters. So you're going to have contours for execution time on one and contours for execution for utility on the other. Now, you're going to have some place on the contours for execution time that have the best possible value for utility. Let me give you an example of what I'm talking about here. Suppose I have a contour map like this. Am I on? I think I turned it off. Let me get back on. Okay. Suppose I have a contour map like this, and I have some contours. Now, I don't know exactly what the contour is going to look like, maybe something like this, I don't know. And then I might have my other contour map, the contour map for utility may look something like this. All right. Now, if I look at each brown contour, there's going to be a place where the utility is maximized. Like, for instance, for this brown contour here, you can see this blue contour is tangent at this point. And what that means is that if this is increasing, okay, then that means that this point represents the highest value of utility on this contour here. And that would be the case every place, right? If this utility is tangent here, that means every point here on this brown contour intersects the utility contours here, and these correspond to lower values of utility, right? So you should be able to identify an optimal point on each execution time curve that gives you the highest utility. Right. It might be on an edge point, but you should be able to identify one single point. Right. So you mark that point with an asterisk on your graph. Okay. And that also will enable you to give a graph of execution time versus highest utility. Right. Here, these brown curves will give me the execution time. The blue curve will give me the utility. So I'll get several values where the execution time, utility pairs, and then I'll plot those here. I'll plot the execution time here and the utility here, so you get some kind of graph. What you do expect, of course, is for this to be increasing. If you want to get better utility, you're going to have a higher execution time. But we may be surprised, right? All right. Now, this is all for the interpolation algorithm. For the non-interpolation algorithm, it's somewhat simpler because we only have one number that we're varying. We're only varying m. So here we just need to find execution time as a function of m, utility as a function of m, and then using these two graphs, I can find utility as a function of execution time. Right? So for the interpolation algorithm and for the non-interpolation algorithm, I'll have utility as a function of execution time. So then you can plot these two lines on the same graph and then discuss the implication. You should be able to tell from these graphs which algorithm is better. Right? And so you need to understand what's going on here. So this discussion is important. Don't neglect this. You really need to explain what your results are showing. Right. Now, this optimal insurance premium payout ratio is another consideration. We can use our model now to help the insurer. Right? The insurance company's profit per customer is B times 1 minus PD over A, where B is the policy cost. That's not just small b, it would be small b times the person's wealth, right? That's the amount that they spend on insurance. And then we have this expression here. And we talked about this before. And we also had the insurance company set little a this way. Now, of course, the insurance company wants to set this ratio A to maximize profit. Now, if you want to maximize profit per policy, you'd set B as large as possible. However, but then customers won't buy it, right? So the customer wants to maximize utility, which also depends on the ratio. If the insurance company increases V, the profit per insurance dollar increases, but the customer buys less insurance. So the insurance wants to find the value of V that hits the sweet spot that will maximize the profit per customer. Okay, so let me see that. So I can say that maximizes profit per customer. Now that's going to depend on the customer's wealth. It's going to depend on the customer's death rate and so on. So we'll just do one particular case here. So we'll set t equal 5. That means in our case, the customer is 50 years old, and set some reasonable values for the wealth and for B plus C. All right. So this is the total expenditure. You can set it as something reasonable, 60%, 70%, whatever you want to set. Justify your values that you use, and make a graph of optimal B versus V. All right. You have enough information to find the optimal B for each fixed V. All right. How do you find the optimal B? Well, we had that equation up top for the optimal value of B, right? This is the equation for optimal value of B. Okay. So, and this W actually depends on V, and I guess this A also depends on V. Right. So B is going to depend on V. So you'll have to make several solutions of that equation. Right. Now recall that in practice, B must be between 0 and 1. If you get a value of little b that's not between 0 and 1, you either have to cut it off at 0 or cut it off at 1. So then let me just say that. So if B exceeds these limits, then truncate value. Right. If you get B as negative, that means that the best value that's conceivable, that's practical, would be 0. Right. Now here we have B. Now once you have B, you can find the profit. So make a graph of profit versus V. So use 2 to do 3. Okay. So this profit assumes the customer will choose their best value of B. And then discuss your results. Do your results make sense? What are the implications for the insurer? Okay. Now, I did mention that I was going to show you how to use Google Colab to help you with the debugging. If I go here and I do colab.research.google.com and I upload my notebook, see if I can find it. Let's try this one here. I think this is the one I'm working on. Now, the problem with giving things to ChatGPT is you have your code all separated. Now, what you can do is you can go to File, Download, and then download.py. And that will download your file as a single Python file. Now, if you know about Spider or VS Code, then you can use the debugger in Spider or VS Code. But you can also use this to query ChatGPT. Rather than having to paste separate cells, you can just copy your code, and you probably want to remove the comments, or you can keep the comments if you want, and then just paste it into ChatGPT, right? So, or any other AI program. So if I just show you, if I download this .py file, then what it gives me is the file, which I can actually read as a text file. Here I'm going to open it with my Notepad++. And you can see it's a single text file. And AI understands this LaTeX. So you can paste this all into LaTeX. It may be easier than pasting pictures. I think that AI will have an easier time interpreting this than it does interpreting pictures. All right, so have fun with this assignment. Let me know what problems you run into. This is certainly a stretch, but I hope that this is a good experience for you. Okay, bye-bye.